Hello everyone. In this video we're going to talk about trigonometric substitutions. So before, when we were normally using the substitution method, we used to have a formula or an integral of the following form. It was like the integral of f of some function gx that it was composed times g prime of x dx. And so as you can see, there's some sort of chain rule that is involved inside of that function, and so it's easy to think that we're just essentially going to get back the original antiderivative for the function f somehow. But once we recognize that f has that basic antiderivative, and we could know how to approach just the antiderivative of f more easily, then what we do is we follow the substitution method steps. We define u as g of x, and then we recognize that if that is u, then the derivative of u with respect to x is going to be g prime of x, and then from that we can say, oh, okay, so du is going to be g prime of x dx, and then we're going to plug that here in this formula. We're going to plug it on the main formula, and we're going to get an integral f of u du, and then we're going to be able to solve the integral of f of u du. And once that we solve that, then we return to the original variable in terms of just x. That is just regular substitution. Now, we're going to go with reverse substitution. In reverse substitution, we're going to start with a very difficult integral from the form just integral of f of x dx that we don't know how to approach, but that we can observe has a relationship that could transform the integral into a more easy to solve integral if we change variables. The steps that follow are very similar. Now we're changing the inner variable for a function g of u, and then again we're recognizing that the derivative of x with respect to the u is going to be g prime of u. Hence we can replace the x for g prime of u du. Notice that is the reverse of what we were doing before. At the end, we're going to end up with a formula in terms of u, but it's going to be some sort of chain rule situation now back. And once again, we expect that this is something that once that we are able to solve, then we can return to the original variable in terms of x. Well, now let's see how reverse substitution really look, and how we can use in particular this for trigonometric substitutions, which are going to be the main examples of these reverse substitutions. So we have a couple of expressions that we're going to be identifying where we can use trigonometric substitution, and is if we have an expression of the type square root of a squared minus x squared, or a squared minus x squared. It doesn't necessarily need to have the square root. Then we're going to be using x is equals a sine of theta. Okay? And we need to take into account that we're going to probably be using the 1 minus sine square equals cosine square identity. In the same fashion, if we have a term a squared plus x squared, or square root of a squared plus x squared, then we're going to be using x is equals a tangent of theta. And likely the identity that is going to come into play is going to be 1 plus tangent square of theta is equals secant square of theta. The last is going to be if we have x squared minus a squared, and that or the square root of x squared minus a squared. In that point, we're going to have a equals secant of theta, and then we're probably going to be using the identity secant of theta minus 1 equals tangent square. Okay, so remember this type of expression, because if you see this in an integral, then you know that immediately it has to be related to this type of substitution. Okay, now let's see some examples of this in use. So let me get the board over here. And so we're going to go with the trigonometric substitution for the integral for square root of 4 minus x squared over x squared dx. And so from what we just saw, we just have this term 4 minus x squared, And this implies that we should go with the substitution x is equals to sine of theta. Remember, this is like a squared. So if 4 is a squared, that means that a is equals 2. And so that's why we get 2 sine of theta. Now, if we do that, then the x the theta is going to be, of course, 2 cosine of theta. And the x can be replaced by 2 cosine of theta d theta. And don't forget this one, because this will come back later when we want to go back to the original variable. So for now, let me just go ahead and zoom in this. And now I'm going to be replacing all the factors. So if x is equals to sine of theta, this is going to be 4 minus 4 sine square of theta. And we have an x squared below, so 4 sine square of theta. And now that the x is replaced by 2 cosine of theta d theta. Okay? So we now continue by simplifying a little bit. So notice that the common step is going to be that I factor this number that is over here. So 4, 1 minus sine square of theta. 4 sine square of theta. And then we have the 2 cosine of theta. Notice that 1 minus sine square is going to be cosine square. And so, of course, this is going to be now 4 cosine square of theta and root over 4 sine square of theta, 2 cosine of theta. And I need to do a lot of simplification in here. So the next step is going to be the simplification of this, which is going to be just 2 cosine of theta. But I'm also multiplying by another 2 cosine of theta over here. And I have 4 sine square of theta. And notice that 2 with the 2 is 4. With the 4 is going to go away. And cosine square over sine square is going to be what is left over here. And if you think what that is, this is just going to be cotangent square, right? Cotangent square of theta, which it doesn't have immediately an antiderivative, but I can transform this again to cosecant square minus 1, the theta. And that one does have an antiderivative. So the derivative of cotangent is minus cosecant square. So if we're integrating cosecant square, I'm going to get minus cotangent of theta. And then if I integrate this minus, it's going to be minus theta here, plus a constant. Okay? And so that will be the integral of this. But now the problem is that I need to get back to x. So here's where this sine of theta comes into play. I need to replace whatever this cotangent of theta is, and I need to replace this theta. So from here, there's a couple things that we do. So first, for theta, we do x over 2. It's sine of theta, and that implies that theta is arcsine of x over 2. So now I have this one. So this is this term, but I'll come back to it later when I'm writing my end result. And I also going to now I need to get cotangent, but cotangent is, if you remember, cosine over sine, right? So I can see this one as cosine over sine, and I do have sine. Sine is x over 2, but I need cosine. So to be able to find cosine, the easiest thing that I can do is get my triangle, get the right triangle, and remember that the sine of theta is thinking of a right triangle with an angle theta here, and that this is opposite over hypotenuse. So this is x, this is the hypotenuse equals 2, and so from there we can find out what this is. That, of course, that comes from the Pythagorean theorem, and if we want to find out what this piece is, let me don't go ahead so quick. I'm going to call this B. We have that the cosine of theta is adjacent over hypotenuse, right? So B over 2. But how do I find this B, this length B? Well, I can do it with the Pythagorean theorem. 2 squared is equals to x squared plus b squared. And so this means that 4 minus x squared is going to be b squared, or b is 4 minus x squared. Okay? So that means that the cosine of theta is going to be 4 minus x squared over 2. So now if I have cotangent, which is cosine over sine, you see that it's this over this. So it's going to be minus 4 minus x squared over x. That's what's going to be cotangent. And minus arc sine of x over 2 plus c. Okay, and so now we reach the end of the first example.